Welcome to G Fun Facts Online. In the world of computation, a change is underway. For decades, we've lived in a world of ones and zeros, the binary logic that powers everything from your phone to massive supercomputers. But we're now facing problems so complex that this classical approach is hitting a wall. And that's where we're starting to hear the first real reverberations of a new kind of power. These are the quantum echoes, and they signal a leap towards a future that used to be science fiction, the era of practical quantum computing. Recently, Google's Quantum AI Lab announced a landmark achievement. Using a new quantum processor named Willow, their machine performed a specific computation about 13,000 times faster than the world's most powerful supercomputers could manage. This isn't just a lab experiment. It's a demonstration of a verifiable, beyond classical computation with a direct line to real-world applications. Today, we're diving into the heart of this quantum revolution. We'll explore the bizarre principles that make it possible, Google's journey to this moment, and what a world transformed by this new power might look like. To understand the scale of Google's achievement, we first need to grasp how different quantum computing really is. It's not just a faster computer, it's a completely new way of processing information built on the strange rules of quantum mechanics. Classical computers use bits, which are always either a 0 or a 1. Quantum computers use qubits. A qubit can be a 0, it can be a 1, but thanks to a principle called superposition, it can also be both a 0 and a 1 at the same time. Imagine a spinning coin. While it's in the air, it isn't heads or tails, it's a mix of both possibilities. Only when it lands does it settle into one state. A qubit is like that spinning coin. It exists in a cloud of probabilities until a measurement forces it to choose. This ability to hold multiple values at once is where the power comes from. A classical 3-bit register can hold only one of 8 combinations at a time, like 001. But a 3-qubit register can represent all 8 combinations simultaneously. Every qubit you add doubles the computational space. Google's earlier 53-qubit Sycamore processor could explore a state space of 2 to the power of 53. A number so vast a classical computer can't even represent it. The second key property is even weirder: entanglement. Einstein famously called it spooky action at a distance. When two qubits are entangled, their fates are linked, no matter how far apart they are. If you measure one, you instantly know the state of its partner. Think of it like having a pair of gloves. You put one in a box and send it to the other side of the galaxy. The moment you open your box and see a left-handed glove, you know with absolute certainty that the other box contains the right-handed glove. Entanglement creates correlations that allow for a kind of parallel processing on a scale classical machines can only dream of. The third principle is interference. Like water waves, quantum states can be made to reinforce each other or cancel each other out. A good quantum algorithm cleverly uses interference to amplify the probability of getting the correct answer while canceling out the paths leading to wrong answers. Superposition, entanglement, and interference together allow quantum computers to navigate vast landscapes of possible solutions in a way that's fundamentally impossible for classical ones. So why do we even need them? Classical computers are struggling with certain types of problems whose complexity grows exponentially. Quantum computers are specialized machines designed to tackle these unsolvable problems. They won't replace your laptop for browsing the web, but they could revolutionize fields like drug discovery and materials science. Nature, at its core, is quantum mechanical. The way atoms and molecules interact is governed by quantum physics. Classical computers can only approximate these simulations, which is why developing a new drug is often a slow, expensive process of trial and error. A quantum computer, operating on the same principles, could simulate these interactions perfectly. This would allow scientists to design new drugs atom by atom, predict how proteins fold to fight diseases like Alzheimer's, or engineer new materials like room temperature superconductors or ultra-efficient batteries. They're also perfect for complex optimization problems. Think of finding the most efficient route for a global shipping network, or managing a financial portfolio for maximum return with minimum risk. Quantum algorithms are designed to search through an astronomical number of options far more efficiently than any classical method. But there's a darker side: cryptography. The encryption that protects our online banking and government secrets relies on math problems that are too hard for classical computers to solve, like factoring huge numbers. A powerful enough quantum computer running an algorithm called Shor's algorithm could solve these problems with ease, breaking most of our current cybersecurity. This has sparked a global race to develop post-quantum cryptography, new encryption standards that are safe from both classical and quantum attacks. Google's path to the quantum echoes breakthrough has been a long one. It started back in 2019 when they announced they had achieved quantum supremacy. Their 53-qubit processor, Sycamore, performed a highly specific task in 200 seconds. They estimated it would have taken the world's most powerful supercomputer at the time, IBM Summit, 10,000 years to do the same. The task itself, called random circuit sampling, had no practical use. The point was simply to prove that a quantum processor could do something that was practically impossible for a classical computer. It was a hello world moment for the quantum era. The claim was controversial. IBM, a major competitor, argued that with a different classical algorithm, the task could be done in 2.5 days, not 10,000 years. But even so, the core achievement stood. A quantum machine had done something far beyond the practical reach of supercomputers. The Sycamore processor was an engineering marvel, but it also highlighted the biggest obstacle in quantum computing: decoherence. Qubits are incredibly fragile. Their quantum states are easily destroyed by the slightest interaction with the environment. A stray magnetic field, a tiny temperature fluctuation. This loss of quantumness is decoherence, and it causes errors. While a classical computer might have one error in a billion operations, current quantum computers can have an error in every few hundred or thousand operations. These errors pile up fast, making complex calculations meaningless. This is why we call current devices noisy intermediate-scale quantum, or NISQ, computers. Overcoming this is the central goal of the field. The solution is called quantum error correction, or QEC. The idea is to build redundancy into the system by encoding the information of one perfect, ideal logical qubit across many physical, noisy qubits. By constantly checking on this group of physical qubits, the system can detect and correct errors without destroying the precious quantum information. In early 2023, Google made a huge step in this direction. They showed that by making a logical qubit out of 49 physical qubits, it had a lower error rate than one made from 17 physical qubits. This was the first experimental proof that scaling up could actually stamp down errors. This set the stage for their next, even bigger breakthrough. The goal was to reach the break-even point, where the error-corrected logical qubit is actually more reliable than any of the individual physical qubits it's made from. And that brings us to the breakthrough moment, detailed in late 2025. It centers on a new processor, Willow, and a new algorithm, quantum echoes. Together they mark a shift from the abstract idea of supremacy to the concrete reality of verifiable quantum advantage. Willow is Google's next-generation chip. It boasts 105 qubits, but more importantly, these qubits are much higher quality. The coherence time, how long a qubit can hold its quantum state, jumped from around 20 microseconds in Sycamore to 100 microseconds in Willow. This allows for much longer, more complex calculations. The most historic accomplishment with Willow was achieving below-threshold quantum error correction. By building logical qubits with larger and larger grids of physical qubits, they were able to exponentially reduce the error rate. For the first time, they built a logical qubit that was demonstrably more robust than its individual parts. This cracked a fundamental problem the field had been chasing for nearly 30 years. But hardware is only half the story. You need a powerful algorithm. Running on the Willow chip, Google demonstrated their quantum echoes algorithm. Scientifically, it's a way to probe the chaotic dynamics of a quantum system, how information scrambles and spreads among entangled particles. The results were staggering. For this specific task, the Willow processor was 13,000 times faster than the world's fastest supercomputer, Frontier. A calculation that took Willow a few hours would have taken the supercomputer over 3 years. And here's the crucial part. Unlike the abstract 2019 experiment, this result is verifiable. The algorithm models a real physical experiment related to nuclear magnetic resonance, or NMR, the technology behind medical MRI scans. This means the quantum computer's output can be checked against experiments in the real world. This provides a vital anchor of trust, proving the machine is accurately simulating physical reality, not just producing complex noise. To show its practical potential, the team used quantum echoes as a molecular ruler. By comparing the output of their quantum simulation with real-world data from an NMR experiment, they could learn hidden details about a molecule's structure. This points directly to a future where quantum computers become essential tools for chemists and material scientists. This breakthrough is a critical signpost on a much longer journey. Google has a public 6-milestone roadmap to a full-scale, fault-tolerant quantum computer. Milestone 1 was achieving quantum supremacy in 2019. Milestone 2 was the 2023 prototype of quantum error correction. This new work with Willow represents a massive advance toward Milestone 3, building a single, long-lived logical qubit. The ultimate goal, Milestone 6, is a machine with 1 million physical qubits, which could encode about 1,000 highly stable logical qubits. A machine of that scale would be capable of truly revolutionary science. Of course, Google isn't alone in this race. IBM is a major force, also using superconducting qubits and regularly releasing more powerful processors, like their Osprey and Condor chips. Microsoft is taking a different, high-risk path with what are called topological qubits, which are theoretically much more resistant to noise. Amazon, with its Bracket service, acts as a cloud platform, giving researchers access to quantum hardware from various providers, including companies like IonQ, which uses trapped ion qubits. This diversity is crucial, as we still don't know which technology will ultimately win out. As these machines grow more powerful, their impact will be felt everywhere. In medicine, simulating molecules will revolutionize drug discovery, allowing scientists to design new treatments for cancer or viral infections computationally. In materials science, we'll be able to design novel materials from the ground up, better catalysts for carbon capture, more efficient solar cells, or room temperature superconductors that could enable lossless power grids. In finance, quantum algorithms could provide near-instantaneous risk assessments and optimize investment portfolios in ways that are currently unimaginable. And we must prepare for the security threat. As quantum computers get more powerful, the global effort to standardize post-quantum cryptography becomes one of the most urgent tasks in cybersecurity. Google's quantum echoes breakthrough is an inflection point. For years, quantum computing was a distant promise. The 2019 supremacy experiment was a major scientific achievement, but its abstract nature left room for doubt. The demonstration of a verifiable quantum advantage changes the entire conversation. By running a useful algorithm thousands of times faster than a supercomputer and producing results that can be checked against the real world, Google has laid down a tangible marker on the path to a useful quantum computer. More importantly, the breakthrough in error correction provides a credible answer to the field's most daunting challenge. The road ahead is still long. Scaling from a few hundred noisy qubits to 1 million stable ones is an immense engineering challenge. But the echoes are now undeniable. They are the reverberations of a future where we can conquer disease at the molecular level, create new materials to solve our energy problems, and redraw the very limits of computation. The faint whispers of yesterday are becoming the clear, resonant echoes of today. heralding the dawn of a new technological age. Google's leap has brought us one giant step closer, and the world is listening.